In this video, I'll explain the first half of the replicate analysis screen. This video will take you up to the standard offset tab, and then the second video in the series, part 2, will cover the replicate steps in the replicate analysis. When you start up the replicate analysis screen, the only thing you see is the timeline below. This is specific to a mass spectrometer. You can choose the mass spectrometer you have if you're lucky enough to have more than one. And as soon as you choose the mass spectrometer, you see the data points for that mass spectrometer here represented in a timeline. So to understand this graph, we start at the bottom, and the times here are on the left, the right, and the middle. And these times tell you what the time range is on the left side of the graph, middle of the graph, and right side of the graph, respectively. As the graph moves around, you can see the times change, or as I zoom in the graph, the times change. So that's how you find your way in this timeline. That's how you know where you're oriented in time. Above the dates are little black triangles, and those are the correction interval markers. So this is a point in time where a correction interval was started on this mass spectrometer, and here is the start of another correction interval. So this region here is one correction interval. The start of a second correction interval ends the first correction interval automatically. Above the triangles are the scan files. That's these little S's. So if we hover over the S, you can see that a scan file was added on this time by this user. Scan files are done pretty much once a day, so you can approximately see days here. Here we missed a day, here we missed 2 days, that might be a weekend. So you can get a rough feel of the time by looking of where you are in time by looking at these points. Above the scan files are the standard replicates. So the standard replicates are colored according to the graphics that you defined when you defined the standards that you use. So here, for example, we have a green square is an ETH3 carbonate, and we have, what else? A purple triangle is an ETH2 carbonate, and these are all times when those standards were run on the mass spectrometer. So this indicates we did a scan file, then we did a couple of standard runs and a couple of sample runs during this day. Above the standard runs, we see the samples, and if we hover over a sample, you can see the name of the sample, the user that sample belongs to, and the time that sample was run. So if we want now, we can actually select something from this list to get the rest of the data analysis working. So I'll select this point here that we were looking at. And there's two things to notice here. Well, there's actually a lot of things to notice here, but the two things to notice are that the replicate information that we saw from the tooltip here is now printed permanently here, so you don't have to wonder which thing that you've selected. You can get the information right there. You can also select standard runs here, and you'll see the name of the standard instead of the sample. And the other thing to notice is that the selection of a sample or the selection of a standard automatically also selects a correction interval. So the fact that we selected this point here means that this correction interval is the one that's currently being used. That's important because as we're correcting this sample run, all of these standards in this correction interval may be used for the correction process depending on the parameters and how they're set. So this is essentially the limits of standard runs that can affect this sample correction. Okay, since we've selected a correction interval, the correction interval is shown up here, and this is the start of the interval and the end of the interval, and you can see if I hover over this, the date is the same. And for this correction interval, we've turned on one replicate analysis. In this particular case, we're using ETH-PBL analysis for all replicates that are done in this correction interval. And below that are the steps that are taken in order to do an analysis. This will be explained more in the next video, but an analysis is basically made up of a series of steps of calculations, and that is one analysis is a series of steps. So we'll explain that in the next video in more detail. And then below that is errors that may exist in the correction interval. So even though I've selected this sample here, this standard here might have an error in the database. There might be something not selected or something there that is necessary to calculate that. In that case, an error message will appear here. So this is an overview of all the errors that may be affecting your corrections in this particular correction interval. Right now we have no error messages reported. That's hopefully the usual case, and we can just continue from there. On the right now we have a single tab here, and it shows us the standard offsets. The standards you see in this graph are the same as the standards you'll see down here in this correction interval, and they're graphed in the same order, and they're also sorted by time the same way these are. So if you look, for example, here we see a cluster of orange points, and here's a cluster of orange points. They're basically the same. This graph is a graph of the offsets of these standards, the measured value from their expected value. It may be easier to explain this by clicking the absolute button though. So if I click in absolute mode, if I put the window in absolute mode, you can see the green line and the red line, yellow lines. These lines are the lines where a particular standard should be measuring for carbon, 13 carbon. So the green standard, which is the ETH3 carbonate, should have a carbon value approximately here. And then you can see that the carbons, or the samples that we measured, the standards that we measured, are actually below this line, and they're always below this line. The reason for this is that we're still looking, the value that we're looking at is the PBL corrected value. We're not looking at the final value, so these values have not yet been drift corrected. They've only been PBL corrected. So it's kind of expected that these values don't actually fall on the line, and you can see that this is true for all the other values as well. They're all slightly below the lines, although these are a little closer down here. So when we view in relative mode, all we're doing is looking at the subtraction of these two things, the difference between these two things. So you can see also on this graph that all the points tend to fall below the expected values, which, as I said, is normal. We put this back in absolute mode. Now we have a list of various things that have been calculated by our data analysis for all these standards. And in this list, we see that there's another carbon value, and this is marked as final. Final means that this is no longer going to be corrected. This is the final value after all corrections, which means that this already includes the drift correction, whereas this one didn't. So if I select this value to look at, you see that the greens have all popped up and are now very close to the line. So we've sort of watched an animation of our acid, or not the acid, the drift correction happening for all the standards in this correction interval. So this graph can give you a good quick overview of how accurate your mass spectrometer is running for the various values. And there are many values here. Any value from the data analysis that could be compared to a standard value is listed here. And the order is a little strange, but the order is determined by the order in which they're calculated. So these values here are calculated by these steps here, and they're in the same order that you would find them over here calculated. That's about it for this screen, that you can use the absolute and relative mode here. We're going to move on to part 2 of this. We'll show how the steps actually work and how you can see every step of the way in the various analysis processes.